Hello viewers, in today's class we are going to take up an important type of integral, and the integrals are of the type. Here we have to integrate 1 over a plus b sin x. Here we have 1 over a plus b cos x. Here we have 1 over a sin x plus b cos x, and here we have 1 over a sin x plus b cos x plus c. Now in this class we are going to study the method how to integrate a function which is of these types, right? So for example, let us take this one, right? So here I would like to mention one important thing, that to evaluate these integrals we have two important identities from trigonometry, right? Or in other words, we can say that the application of those trigonometric identities are used to evaluate these integrals. So the first one is sin x can be written as 2 tan x by 2 divided by 1 plus tan square x by 2. So this identity gives us the relation between sin x and tan x by 2. Similarly, the second identity is cosine x is equal to 1 minus tan square x by 2 divided by 1 plus tan square x by 2. So these two identities are used in evaluating the integrals of these types, right? Now let us evaluate this integral. So here we see that it is 1 over 5 minus 4 sin x, and this integral is of this type. And if we compare these two integrals, we get a is equal to 5 and b is equal to minus 4, right? So let us call this integral as I. Now see, to evaluate this integral we have to make use of these two important trigonometric identities, right? So here see, sin x appears here, so we'll substitute sin x is equal to 2 tan x by 2 divided by 1 plus tan square x by 2, right? Okay, so here we'll substitute this value of sin x. So this integral now becomes 1 over 5 minus 4 times of sin x, that is 2 tan x by 2 divided by 1 plus tan square x by 2, and here we have dx. Now if we simplify it, we get, see, 1 plus tan square x by 2 goes to the numerator, and here we have 5, that is 5 ones are 5 times tan square x by 2, and minus this is 4 times 2, that is 8 tan x by 2, right? And here we have dx. Now this integral becomes 1 plus tan square x by 2 and divided by, see here now we cannot simplify it further, so we can write for 1 plus tan square x by 2, we can write sec square x by 2, and here we have 5 plus 5 tan square x by 2 minus 8 tan x by 2, right? Okay, now here we'll now make use of the substitution method, and let us substitute y is equal to tan x by 2, right? Now dy over dx is half sec square x by 2, and 2 dy is equal to sec square x by 2 dx. Now for this expression we can substitute 2 dy. So here we have 2 dy, and in the denominator we have 5 plus 5y square minus 8y, right? Now this can be further written as 2 times integral of 1 over 5y square minus 8y plus 5. Now see, this integral is now reduced to the quadratic form, right? So what we will do, we'll try to make it a perfect square by addition or subtraction of some number. So here if we take 5 common, so we have 5, 2 by 5, and this can be written as dy over y square minus 8 over 5 y plus 1. Clear? Now this expression can be written as y minus 4 over 5 whole square, right? So we have a square, that is y square, then we have 2ab term which is minus 8y over 5, and then we have 16 over 25, so which can be compensated by writing minus 16 by 25, right? So, and here we have plus 1, right? So this expression has now become this expression, right? So converting it into this square term. So now this is further written as y minus 4 by 5 square, and this is 25 ones are 25 minus 16, that is 9 over 25. Now this can be written as y minus 4 by 5 whole square plus 3 over 5 square, right? So now this integral can now be written as 2 over 5, and we have dy divided by y minus 4 by 5 whole square plus 3 by 5 square, right? Okay, now if we put t is equal to y minus 4 over 5, then this implies dt is equal to dy, and this integral can now be written as 2 by 5 and dt over t square plus 3 over 5 square, right? Now this integral is now reduced to the known form. And what is the known form? The known formula is we have dx over x square plus a square can be written as 1 over a tan inverse x over a, right? So this integral can now be written as 2 by 5 times 1 over a. For a we have 3 by 5. So here we have 3 by 5, and then we have tan inverse t over 3 by 5 plus c, and c is the constant of integration, right? Now this can be written as here 5 and 5 get cancelled, so we have 2 over 3 and tan inverse 5t divided by 3 plus c. Now for t we can write y minus 4 by 5, so it is 2 by 3 tan inverse 5 by 3 multiplied y minus 4 by 5 plus c. Clear? Okay. Now this is 2 by 3 tan inverse, and multiplying these two terms by 5 by 3, so we have 5y by 3 minus 4 by 3, right, plus c. Now this can further be written as 2 by 3 tan inverse, this is for y we have tan x by 2, so we have 5 by 3 tan x by 2, right, minus 4 by 3 plus c. So this is the required integral of this function. So therefore the integral of this function 1 over 5 minus 4 sin x is given by 2 by 3 tan inverse 5 by 3 tan x by 2 minus 4 by 3 plus c. C is the constant of integration, right? So this completes our solution. And now suppose we have to find the integral, the definite integral from 0 to say pi by 2 of this function, right? Now here suppose instead of finding out this, we have to find this integral, that is the definite integral. So what we will do in that case, we'll proceed to find the integral of this function as we have done just now, and we'll arrive at this result, right? And then we'll simply substitute the limits here, right? So this integral, this definite integral now becomes this. We simply evaluate this function, because when we find the definite integral, we do not have this constant of integration because it get cancelled. So we have here the lower limit 0, and here we have the upper limit pi by 2. So now let us evaluate this function at these 2 points. So here if we substitute pi by 2, then we have 2 by 3 tan inverse 5 by 3 tan pi by 4, because here x is pi by 2, so it becomes pi by 4, minus 4 by 3 and minus, right? Then we have minus, because we know that if we want to find the definite integral from a to b f of x dx, then we have fb minus fa, right? So here we have minus, and if we substitute x equal to 0 here, we have 2 by 3 tan inverse, and tan 0 is 0, so this term becomes 0, and here we have 0 minus 4 by 3, right? Okay, so now this becomes 2 by 3 tan inverse, this is 1, so 5 by 3 minus 4 by 3 becomes 5 minus 4 is 1 over 3, so here we have 1 over 3, minus 2 by 3, and we have tan inverse minus 4 by 3, right? Okay, now taking this negative sign, here we get 2 by 3. We'll take 2 by 3 common, so we have tan inverse 1 over 3 plus tan inverse 4 by 3, right? And if we apply the identity, that is tan inverse x plus tan inverse y is equal to tan inverse x plus y divided by 1 minus xy here. So we have 2 by 3 tan inverse, and this is 1 by 3 plus 4 by 3 divided by 1 minus 1 by 3 times 4 by 3, right? Okay, so now this becomes, if we simplify it, then we'll have 2 by 3 tan inverse, and this is 12 plus 3 15, this is 5 by 3, right? So this is 5 by 3, and this is 9 minus 1, 9 minus 4, that is 5 by 3, right? And these two get cancelled, so we have 2 by 3 tan inverse 1, and tan inverse 1 is pi by 4, so this is 2 by 3 multiplied pi by 4, and this is pi by 6, right? So viewers, the indefinite integral of this function is 2 by 3 tan inverse 5 by 3 tan x by 2 minus 4 by 3 plus c, and the definite integral, if we take the limit from 0 to pi by 2, then the value of this integral is pi by 6, right? Now let us evaluate an integral of this form, that is 1 over a plus b cos x. So here we have 1 over 5 plus 4 cos x. So if we compare, we get a is equal to 5 and b is equal to 4. Now again we'll make use of this identity, right? In this example we had used this identity, and now we'll make use of this one. So here I becomes 1 over 5 plus 4 times cos x, and it is 1 minus tan square x by 2 divided by 1 plus tan square x by 2, right? So here we have this expression, and now taking LCM, that is 5 times 1 plus tan square x by 2 is 1 plus tan square x by 2, and because this term goes to the numerator, and here we have 5 times 1 plus tan square, 5 times 1 plus tan square x by 2 plus 4 times 1 minus tan square x by 2, and 1 plus tan square x by 2 is sec square x by 2, because we know 1 plus tan square theta is sec square theta. Now here we have 5 ones are 5 times tan square x by 2 plus 4 times 1 4, 4 times tan square x by 2 is 4 tan square x by 2. Now this is sec square x by 2 dx, and 5 plus 4 is 9, and 5 minus 4 is 1, and we have 1 tan square x by 2. Here we have 1, right? Now we'll substitute y is equal to tan x by 2. So dy over dx is half sec square x by 2, and 2 dy is equal to sec square x by 2 dx. So for this term we have 2 dy, this 2 dy, and this is 9 plus y square, because y is tan x by 2, right? So this integral now becomes 2 times dy over 3 square. This is written as 3 square plus y square. Now this is a well-known form, because dx over x square plus a square is 1 over a tan inverse x over a, right? So this can be written as 2 times 1 over 3, and we have tan inverse y over 3 plus c, right? And for y we can write tan x by 2. So this can be written as 2 by 3 tan inverse 1 by 3, and for y we have tan x by 2, right, plus c. So this is the integral of this function. So viewers, the integral of this function is given by this expression. Now suppose again if we want to find the definite integral, right? Here we have evaluated the indefinite integral, and c is the constant of integration. Suppose we wish to find the definite integral 0 to pi by 2 of this function 5 plus 4 cos x dx, then what we will do, we'll find this expression by this method, and then we will simply substitute the limits and find the difference, right? So we have 2 by 3 tan inverse 1 over 3 tan x by 2, and plus here we will not have the constant of integration, and we can write here 0 to pi by 2, right? So let us evaluate this function at pi by 2. So we have 2 by 3, and this is tan inverse 1 by 3, and see this is tan pi by 4 because x is equal to pi by 2, and tan pi by 4 is 1, minus this is 2 by 3 tan inverse 1 by 3, and here if we substitute 0, so this becomes tan 0, right? And this is 2 by 3, and tan inverse, this is 1 tan pi by 4, so we have 2 by 3 tan inverse 1 by 3, and tan 0 is 0, so this whole term becomes 0, and tan inverse 0 is also 0, right? So here we have 0. So tan inverse 0 is 0, so this expression now becomes 2 by 3 tan inverse 1 by 3. So this is the definite integral from 0 to pi by 2 of this function. Now let us take an example of this form. Here we have to integrate 1 over square root of 3 sin x plus cos x. Now if we compare this form with this problem, then we see that the value of a is root 3 and the value of b is 1, right? Okay, now here we see that in the first form we had only sin x, in the second form we had only cos x. Now in this form we have both sin x and cos x, so here we'll make use of these two identities, right? So this integral now becomes 1 over square root of 3. For sin x we can write 2 tan x by 2 divided by 1 plus tan square x by 2, plus for cos x we can write 1 minus tan square x by 2 divided by 1 plus tan square x by 2, and here we have dx, right? See, the LCM or the denominator of this fraction and this fraction are same, so we can write this expression as 2 root 3 tan x by 2 plus 1 minus tan square x by 2 divided by 1 plus tan square x by 2. Now this can be written as 1 plus tan square x by 2 is sec square x by 2 due to this identity. 1 plus tan square theta is sec square theta. So taking this expression to the numerator, and here we have sec square x by 2, and in the denominator we have 2 root 3 tan x by 2 plus 1 minus tan square x by 2, right? Okay, so once we have this expression, by making use of these two identities, we can now substitute y is equal to tan x by 2, right? So dy over dx is half sec square x by 2. 2 dy is equal to sec square x by 2 dx. Clear? Okay, now this expression now becomes, or this integral becomes 2 dy divided by 2 root 3 y plus 1 minus y square, right? So now here we see that we have a quadratic function in the denominator. Now this integral can also be written as 2 and here we have dy, and then we can write y square. This is the minus y square plus 2 root 3y plus 1, right? Okay, now converting this quadratic function into a square, we have y minus root 3, sorry, here we have plus, and here we have the negative sign, so we can write minus y plus square root of 3 whole square. Then we'll have minus y square, and then okay, here we'll have the negative sign, right? Because the negative sign will have 2 root 3y, due to this negative sign we'll have plus 2 root 3y. So this is minus y square and plus 3, so here we should write minus 3 and plus 1. So this becomes 2 times integral dy over now this becomes see, y minus root 3 whole square is equal to y square plus 3 minus 2 root 3y. So if we multiply this expression by negative sign, we get minus y square, and then we'll have minus root 3 and plus 2 root 3y. So here we must have the positive sign, right? Okay, so now this is 3 plus 1 4, and this is 4 minus y minus root 3 whole square, right? Okay, now let us again put t is equal to y minus root 3. So dt is equal to dy, and here we have 2 times integral dy over 2 square. This 4 is 2 square minus, here we'll have t square, and here we'll have dt, right? Now this integral becomes a well-known form of the integral, that is 1 over a square minus x square dx, and this is equal to 1 over 2a log, and here we have a plus x divided by a minus x, right, plus c. Now this integral, making use of this formula, we have 2 times, then we have 1 over 2 times 2, because a is 2 here, and for x we have t, so this is log, and here we have 2, plus for x we have t, so this is 2 plus t divided by 2 minus t, right, plus c, and here 2 and 2 get cancelled, so we have half log, and this is 2 plus for t, we have y minus root 3, right, y minus root 3, and here we have 2 minus y minus root 3, so we have minus y plus root 3 plus c, and for y we can again substitute tan x by 2, so this is half log 2 plus tan x by 2 minus root 3 divided by 2 minus tan x by 2 plus root 3 plus c, right. C is the constant of integration.